right, welcome back, everyone. So in our last video, we stopped with this reaction up front of potassium phosphate, aqueous, reacting with nickel chloride, both aqueous. And our final products in this double displacement reaction were nickel phosphate, which is a solid, and potassium chloride, which is aqueous. We determined the states from the solubility rules. This is not only a double displacement reaction, but it's also a precipitation reaction because of the because a solid is produced. So we ended with this balanced molecular equation for that reaction. And that's very helpful to scientists. But what can also be helpful is to know what species, what's actually swimming around in solution in your beaker when you do this reaction. If you remember, ionic compounds that are soluble, when they're soluble, they don't just stay as intact molecules, they break apart into their cations and anions. Things that do that are ionic compounds that are soluble, strong acids, and strong bases. Everything else stays together as an intact molecule. And it can be helpful for scientists to know what is actually swimming around in solution when doing this reaction. So when looking at my balanced molecular equation, I see I have three things that are aqueous. Get my pen again. I have three things that are aqueous. So in my reaction beaker, I really don't have potassium phosphate swimming around in solution as an intact molecule of potassium phosphate. I have potassium ions and I have phosphate ions that are swimming around in solution. Remember, the phosphate's a groupie, it's a polyatomic, so that 4 comes along for the ride. Okay. So it can be instructive for chemists to take a balanced molecular equation and write something that's called the ionic or total ionic equation. That is essentially taking your molecular equation and everything that is aqueous gets split up into its cations and anions. Things that are solid, like in this case, the nickel phosphate, things that are pure liquids or gaseous compounds stay together. So I know the answer for the ionic equation for this molecular equation is on the next slide, but let's talk about how it was derived a little bit before going there. So we said that in the ionic equation, everything that is aqueous gets split into its cations and anions. So for potassium phosphate, I have potassium ions and I have phosphate anions, okay? Which is correct. How many potassium ions do I have swimming around, though, from this potassium phosphate? I have, if you remember when we balanced the chemical equation, we had 2 times 3 or 6 potassiums. So when I write my balanced ionic equation, I not only write the ion and the charge, but I have to put how many of that ion I have. Because of the 2 out front, and because of that subscript 3, I have 2 times 3 or 6 potassium ions that are aqueous. It's supposed to be an AQ. Okay. Plus, I'm looking at my phosphate anion. How many phosphates do I have from this part of the reaction? I have 2. So I'm going to put a 2 here. I have 2 PO4 anions that are aqueous. And as I go on doing this, I am sure, at least I hope, my writing will get a little more neat. So that's the cations and anions from splitting up from potassium phosphate. Now we need to do something similar with nickel chloride. Why do we need to split that up into cations and anions? Well, because it's aqueous. We got that from the molecular equation. So I know I've got nickel cations. And from my balanced chemical equation, I see that I have 3 of them. So I have 3. Ugh, that's horrible. I'm gonna have to work on this. I have 3 nickel cations that are aqueous. Then I've got chloride anions. And how many of those do I have? I see that 3 out front, but there's also this 2 back here. So just like what we did with the potassium, I'm going to have to multiply. I'm going to have 3 times 2, or 6 chloride anions. So that's the reactant side of this equation for the ionic equation. Things that are aqueous are split apart into their cations and anions. So for the product side, for this nickel phosphate, do I have to split it up into its cations and anions? I see that it's a solid, and according to my rules, I don't separate things that are solids, liquids or gaseous. So in my total ionic equation, this bad boy just stays together. So in the total ionic equation, you would just write that as it is. But you would, however, split apart the potassium chlorides because they are aqueous. And specifically, there would be 6 potassium ions and 6 chloride anions. So what I just said there verbally is probably better shown right here, typed out. So this would be the total ionic equation from that previous molecular equation. And basically, what does that do? That shows the species what are actually swimming around in solution in your beaker when doing this reaction. So when looking at this total ionic equation, you see there's a lot of things going on, lots of ions around. But you can, I'm sure, see that some ions that are on the reactant side, like the potassiums and the chlorides, those same ions are also on the product side. So when you have that happen in your total ionic equation, and with the equations we'll be doing in this class, your total ionic equations are almost always going to have some ions that cancel out. When you encounter ions in your total ionic equation that are the same on both sides of the equation, number, charge, and state, then they cancel out. It's like saying if you have 2x on one side of the equation and 2x on the other side of the equation, they cancel out. So doing that, canceling out ions that are the same on both sides of the total ionic equation gives you something that's called the net ionic equation. So essentially going from the total to the net is just taking out the ions that are the same on both sides and writing down what's left, which is what is right here. Okay? So there will be problems like that on the exam. I have here that we're going to do an example from the worksheet. I'll probably do one of those in a different video, but I would encourage you to look at the examples on the worksheet, work them, check your answers, and feel comfortable being able to not only predict double displacement reactions and write the molecular equation, but to write total and net ionic equations. So one more point I'm going to make in this little video before stopping is when you write total and net ionic equations, it's really important to note the state, that's what's in parentheses here, and charge of each species. And why is that? Is that just me being picky? Well, no, that's not just me being picky. That's because state and charge is important because it can speak to the reactivity of an atom or molecule. For example, sodium. I think I gave this example maybe towards beginning of chapter 5 or something. Sodium as a solid metal, just plain old sodium atoms, is pretty reactive. Reacts violently upon water and oxygen. You know, it's not something you'd want to be playing around with in your kitchen. But sodium as an ion, something that has lost an electron, is very stable. This is the form of sodium that is in table salt, sodium chloride. So even though both of these substances are sodium, they have the same number of protons, sodium as an element, as a neutral element, is a lot different than sodium as an ion. I would much rather play with a cute little puppy than whatever this is. So this is just my way to remind you that when doing these total and net ionic equations, it's really important that you note not only the atom or the species involved, but the charge and the state.